Welcome to Luca is a Billionaire, where the only thing I invest in is your answers.
You begin by locking down three essentials: linear algebra, basic quantum mechanics, and practical Python skills. Learn vectors, matrices, and eigenvalues, then implement simple examples with NumPy so theory becomes code. Once comfortable with two-level systems and measurement, install Qiskit or Cirq and run a Hello World circuit. Make sure to combine short theory sessions with hands-on notebooks. Alternating strengthens intuition and muscle memory. Start small and iterate. Build single-qubit circuits before tackling entanglement or multi-qubit noise models. Once done with basics, expand into algorithms and hardware-aware thinking. Implement Deutsch-Jozsa, Grover, and the Quantum Fourier transform on simulators to learn resource counts and circuit depth. Make sure to study noise, model decoherence channels, and try error mitigation techniques on real device backends. Parallel that with hardware literacy. Understand superconducting versus trapped ion trade-offs, qubit connectivity, and control limitations, because real experiments shape algorithm design. Alternate building algorithms with profiling on actual backends to close the theory. Finish by delivering an end-to-end project. Design an experiment, simulate it, and run it on a cloud quantum processor. Explain choices, log metrics, and produce reproducible notebooks so you can iterate. If results diverge, first verify calibration and backend job metadata, then simplify circuits to reduce depth and gate count. Make sure to instrument experiments with noise probes and compare simulator to hardware expectations. Persist. Hardware limits are common, but systematic debugging, calibration checks, noise attribution, and circuit pruning yields progress.
Thanks for watching and please subscribe. It's the best investment you'll ever make.